Hi, ma'am. This is T. Kushi from IDA, and my topic for Tech Talk for data structures is algorithms and data structures for new models of computation. So, coming to the definition, data means collection of raw facts. Data structure is representation of the logical relationship existing between individual elements of data. Data structure is a specialized format for organizing and storing data in memory that considers not only the elements stored but also their relationships to each other. Data structure affects the design of both structural and functional aspects of a program. Program is equal to algorithm plus data structure. You know that an algorithm is a step-by-step procedure to solve a particular function. So now let us see the classification of data structure. So data structure is classified into primitive data structure and non-primitive data structure. In primitive data structure, you're having integer, character, float, and pointers. And in non-primitive data structure, it is further divided into arrays and lists. In arrays, you will have one-dimensional array, two-dimensional array, and multi-dimensional arrays. And in lists, you will have a linear list and non-linear list. Coming to linear list, you will have stacks, queues, and linked lists. And coming to non-linear list, you will have trees and graphs. So coming to stacks, it is based upon the principle of first in last out. And coming to the queue, it is based upon the principle of first in first out. And coming to the linked list, so it is having two data fields in a particular list. So one is data field and the other one is address field. So it is used to link one list with other. And coming to trees and graphs, these are nonlinear lists. So primitive data structure, there are basic structures and these are directly operated upon by the machine instructions. Data structures that are directly operated upon the machine level instructions are known as primitive data structures. Integers, float pointing numbers, character constants, string constants, pointers, etc. fall in this category. Non-primitive data structures, these are more sophisticated data structures. The data structures that are derived from the primitive data structures are called non-primitive data structures. The non-primitive data structures emphasize on structuring of a group of homogeneous or heterogeneous data types. So here homogeneous means same and heterogeneous means different. Linear data structures. Linear data structures are a kind of data structures that has homogeneous elements. As I already told before, homogeneous means same type. The data structure in which elements are in a sequence and form a linear series. Linear data structures are very easy to implement since the memory of the computer is also organized in a linear fashion. Some commonly used linear data structures are stacks, queues, and linked lists. Nonlinear data structures. A nonlinear data structure is a data structure in which data item is connected to several other data items. Nonlinear data structure may exhibit either hierarchical relationship or parent-child relationship. The data elements are not arranged in a sequential structure. The different nonlinear data structures are trees, and graphs. Description of various data structures using arrays. An array is defined as a set of infinite or finite number of homogeneous elements of same data type. It means an array can contain one type of data only. That is, it can have all integers, all float numbers, and all characters. An array with one row or one column is called as one-dimensional array. It is finite collection of n number of elements of same type such that it can be referred by indexing. The syntax elements are stored in continuous locations. Element X to define one-dimensional array is, the syntax is as follows: data type, array name, and size, where data type is a value what an array can store. It can be an integer value, it can be a char value, or it can be a float value. Array name is used to identify the array. Size. The maximum number of elements that the array can hold is called the size. And always the array size is given in square brackets only. Simple declaration of an array is as follows: int array of 10, where int specifies the data type or type of elements an array can store. Array is the name of array, and the number specified inside the square brackets is the number of elements an array can store. This is also called as the size of the array or length of the array. So, representing a linear array in memory. The elements of linear array are stored in consecutive memory locations as shown in the below. So, as shown in the figure below, you will notice that the array elements are always stored in a continuous memory location, that is one after the other, and array elements can be accessed or can be printed by using its index. So by default, the array index starts at 0 and ends at n-1 elements. The elements of array will always be stored in the consecutive, that is continuous memory locations. The number of elements that can be stored in an array is nothing but the size or the length of the array. It can be given by the following equation: upper bound minus lower bound plus 1. So for the above array which was represented in the previous slide, the size of the array would be 9 minus 0 plus 1, that is 10, where 0 is the lower bound of the array and 9 is the upper bound of the array. Array can always be read or written through a loop. You can use for loops or while loops to read or write an array. So for using for loop, scanf is used to give the input values at the runtime, and printf is used for printing the values using array indexes. So coming to the introduction of data structures and algorithms in how are they used in standard models. So in the earlier days of computer science, the community settled on a simple standard model of computing and a basic canon of general purpose algorithms and data structures. The standard model of computing has one processor that performs a single instruction at a time, memory that is uniformly accessible with a negligible latency, readily available persistent storage with significant latency, input and output that is insensitive to content or context and orders of magnitude slower, resources and connections that do not change, and no significant concerns about energy use or component failure. The canon of data structures and algorithms include lists, quicksort, string search, trees, and hash tables. The most recent general-purpose data structure is the skip list, which was invented in 1989. Work continues in specialized areas such as graphics, distributed systems, user interactions, cyber physical systems, and artificial intelligence. Except perhaps for quantum computing algorithms, general textbooks have the same model and cover similar topics. Today, we expect computer systems distributed across the entire Earth to function as a single unit, in spite of speed of light delays, which often requires careful catching. So, examples of algorithms and data structures. Our first example is reservoir sampling. For the first algorithm, consider a stream environment, that is, items arrive one at a time. The program does not know how many items will arrive over equivalently. An answer may be required after an unspecified number of items has arrived. Since we do not know how many items there will be, we limit resources to be a constant amount of memory, plus a counter that requires long n bits. As a real-world example, imagine a network of tiny series detecting pollution. Randomly, a sample is requested for every sensor in the network. The tiny sensors cannot store many samples, and for statistical purposes, all samples must be equally likely. So here you can see the picture for reservoir sampling. The problem is to randomly select an item from a stream of items unknowing length using a near constant amount of memory. All items must have an equal chance of being selected. The challenge is to choose one of the items randomly, with all items having an equal chance of being chosen. If the number of items is known beforehand, one could generate a random number in the range of the number of items. Alternately, one can store all items, possibly in some data structure that can grow as needed, and choose one when needed. Neither of these standard solutions satisfy the constraint of not knowing the number of items beforehand. It requires storing the item chosen so far and a counter n that holds the number of items from the stream so far. So, to begin, store the first item and set n to 1. For each new item, replace the chosen item by the new item with probability 1 by n plus 1 and increment the value of n. Adapting the reservoir sampling algorithm allows the following elegant program structure. For every item, if this item is prime, then decide whether to keep it or not. As several authors have pointed out, reservoir sampling can be easily extended to pick m items at random for a stream. The insight is to keep a new item n plus 1 with the probability m by n plus 1. If we decide to keep a new item, randomly choose one of m items to replace. So coming to the next example of an algorithm, that is majority in a stream. The next algorithm we consider also takes place in a stream environment. Suppose items occur multiple times and one of the items is known to occur more than half the time. As a real world example, consider an ad hoc set of tiny low power sensors communicating in a ring that need to select a majority of items. So, although the sensors can pass their items around the ring, no sensor can store all items totally. No sensor even knows the total number of sensors still operating. So, storage is needed for two things: a tentative majority item and an unmatched count. Note that the count is either 0 or positive. Begin by setting the count to 0. When an item arrives, if the count is 0, set the tentative majority item to be the arriving item and set the count to 1. If the count is positive and the arriving item matches the majority item, increment the count. If the count is positive and the arriving item does not match, decrement the count. At the end, the tentative majority item is the majority item if one exists. If no item occurs a majority of times, any item can be the tentative item at the end. There is no guarantee that the item is kept with a plurality. So as you can see the picture, this is a picture of a majority stream algorithm. The problem is to find which item in a stream occurs the majority of times using a near constant amount of memory. In this example, more than half of the items are T. Diagram suggesting the correctness of an algorithm, the majority items can be paired with other items and have some remaining. Every item that is not the majority item can be paired with a majority item somewhere in the stream. That is, the count for each pair of majority and non-majority items will cancel out. Either the non-majority item is tentative and the majority item decrements its count, or the majority item is tentative and the non-majority item decrements the majority item count. In either case, there is at least one majority item that will not be paired. There are more of them, all non-majority items. This item will get a positive count that is not cancelled. So the next algorithm is virtual memory aware heap. Next, we represent an implementation for the classical binary heap that works better with modern memory systems. Binary heaps are used in priority queues and the heap sort algorithms. Typically, heaps are implemented within an array. A node at index I has child node at indexes 2i and 2i plus 1 and a parent node at index I by 2 with one base indexing. The problem is that for large heaps, every level ends up in a different virtual memory page. Thus, traversing from the root to a leaf causes a page fault for almost energy level and occupies a significant amount of cache. The B heap is a modification that allocates significant subtrees in a single tree. Typically, pages are large enough to hold subtrees with a dozen levels. Thus, the number of page faults is reduced up to an order of magnitude using far fewer entries in the cache and page tables. Other variants such as cache, obvious algorithms, implicit k-way heaps, min-max heaps, and Van Emmet Bayes layouts similarly work far better with the actual virtual memory. So this is the picture of virtual memory heap. So the conclusion of virtual memory heap is that when you try to store the same large amount of content in one page, it is not possible. So by default, it will be going to the next pages. So to keep the connection from one page to another page, it is very difficult. So to store large amount of such data, you can store it in the form of subtrees. So sublevels or subtrees. So when you store an information in the form of subtrees or sublevels, you can store almost a large amount of data in one single page, and there will be no problem for the linkaging of data. And by this method, there will be no memory wastage and there will be no page wastage, and there is no problem for linking the pages as well. So coming to the conclusion, new constraints and opportunities on computing such as highly parallel, cloud, and energy-aware computation can lead to novel, elegant, broadly applicable algorithms and data structures. We call for a renewed interest in and resources for research of basic algorithms and data structures. CAM says programmers should be taught some cache-aware data structures and algorithms to understand the benefits of and need for such improvements. So I hope you all understood about the data structures, data structure, classification of data structures, arrays, and primitive and non-primitive data structures, and how data structures and algorithms are being used in new modern world computing. I hope you understand this topic clearly. Thank you so much.